Okay, so we will move on to reactive power without magnetic fields. So till now we have been discussing about reactive power associated with magnetic field or an electrical component that momentarily stores magnetic energy and releases magnetic energy. This is always associated with a reactive power. That is why we used pure capacitor and pure reactor initially to explain the concept of reactive power source and reactive power load. Now, sometimes we encounter situations where loads absorb reactive power without creating any magnetic field at all. This can happen in power electronic circuits where there is rapid switching is happening, or when the current flow is delayed by means of a switching device such as thyristor or MOSFET. If you do that, then reactive power consumption would be there because it creates an angle between voltage and current. So let's see an example with that. Say I have a generator connected. I'm connecting this to a meter here, which is ammeter. This is my ammeter. Then I have a switching device here. It's not mentioned what switching device is this. This is some switching device connected to a resistor like this. Now this is 100 volts, of course effective RMS only. Now this is a 60 hertz source. So this is connected to a resistive load, a pure resistive load of 10 ohms. So without the composition of a reactance, capacitive reactance or inductive reactance, we assume that, or we presume that there is no reactive power associated with this circuit without the switch, because it's a pure resistive circuit. But with this switch, we often see a reactive power associated with the circuit. Say the switch opens and closes its contacts so that the current only flows during the second part of the half cycle, which means what is the second part of or the latter half of the cycle. The half cycle means, see, this is the voltage, right? Now I'm going to switch the circuit such that the current is like this. I'll use another color. Current is like this. Okay, till this point. Then this is the latter half, right? Latter half of this half cycle. Now this is the latter half of this half cycle. So the current is like this. Okay, so the switch opens and closes its contact so that the current only flows during the latter part of each half cycle. So this is 90, this is 0, this is 180, right? This is 270. Okay, now we can see by intuition itself, we can see this forced delay of current with respect to voltage. This causes some reactive power consumption or generation that we'll see. Here it is consumption because it is lagging. The current is lagging the voltage. If we connected a wattmeter or warmeter between the source and switch, say if I am connecting a wattmeter or warmeter here, then say if it is reading some 318 var and 500 watts, what should be the sign of this var? You might have gone through the previous lectures. What must be the sign of this var 318? Is it plus or minus? Anybody? we assign a positive sign if the reactive power is consumed or it is associated with the reactive load. We assign a negative sign by convention if it is a reactive power source. Here the current lags the voltage, so it is reading plus 318 var. Then this is plus 500 watts, right? This is resistive load associated with active power, right? Now this corresponds to a lagging power factor. How will you find the power factor in this case? What is the power factor in this case? How will you find it? Anybody? I have P with me, Q also. How will you find the power factor?
Sir, tan inverse of P by Q.
Oh, that is one way to find it. Otherwise, I can also P divided by root of
P square plus Q square.
P squared plus Q squared. So if I do this, what I am getting? What is the power factor here?
Sir,
Cos phi.
Can anybody calculate this part? The proportion of active power
excuse me,
utilized
sir.
in the, yes.
Sir, I had a small doubt, sir. The var ampere meter, what does it read, sir, actually? Whether it reads BI or the reactive power, sir?
No. See, var meter will read VI sin phi only.
Okay, sir. Means Q value.
Yeah,
the
Q
reactive
only.
power.
Yeah.
Okay.
The other meter will read VI cos phi.
Thank
Okay.
you, sir.
So what is this? What are you getting here? Point?
Sir, 0.85.
Okay. 0.84 or point? I think it's 0.838, right? Then 0.84 maybe. Maybe approximately. Okay, 0.84. So the reactive power is associated with the rapidly operating switch rather than with the resistor itself here. So this is associated with the switch here. But the reactive power is consumed just as if a reactor was present in the circuit, right? If an inductive reactance was present in the circuit, it would have consumed reactive power. So just like that, now also reactive power consumption is there, but that is because of the switching device. Now here,
sir.
Yes, tell me.
Please once again tell how it is lagging, sir. I couldn't understand.
See, here the switching is done. See, this switching, sometimes it closes, sometimes it opens, and rapid switching is done in this period. In this period such that the conduction happens only at this point. The current conduction happens only at this point. And after that it will close. Then again the current conduction will happen at this point. Again it will close. Okay, so at this point it will close. This point it will open. Again it will close, like that. So see, we are not going to analyze the characteristic of the switch now. There are different switches used, which is suitable for that particular circuit according to the requirement. Okay, so you just assume that as a switch, that's all. Now, as of now. So that is why there is a lag coming here. Now, I'm taking another circuit where I have both resistance and capacitance. See, I'm taking a reactance here. Then I have a load having capacitance and resistance. So this is R. This is some XC. So like this. Okay. Now this is my E. This is IL. 8 ohm is XL. Then this voltage is 60 volt. This voltage is 60 volt. This is 5 ohm. This is 12 ohms. Okay, so this is terminal 2. This is terminal 1. Okay, now this figure, from this figure, what is the current in each circuit element. I want to find the current in each circuit element. How will you find the current and the corresponding active and reactive power consumed or generated by each of the elements in the circuit? Say I am first finding the current in the capacitor. Current in the capacitor. What is the current in the capacitor here? Let it be IC. I am representing it by denoting it as IC. What is IC? 60 is the voltage, right? 60 is the voltage. Then divided by 5, which is equal to 12 amps. Now I want to find QC. So here, what should be the sign of QC? What should be the sign of QC in this case? This is reactive power generated. So I will give a negative sign for this QC. Now, how will I find QC? 12 amps is the current, right? Into 60 volt is the voltage across capacitor. It is given 60 volt is the voltage across capacitor. So this will give me 720 var, but with negative sign. Now, how will I find the current in the resistor? IR. 60 is the voltage, again divided by 12 will give me 5 amps. Right. Now, if I want to find the active power P, 5 is the current into 60 is the voltage, which is equal to 300 watts. So I am going with finding the reactive power and active power associated with each component in the circuit, thereby finding the total reactive power and active power consumption of the circuit. That is the approach here. I am not going with a loop currents or using currents and impedances. I am not using currents and impedances here. Okay. Instead, I am using voltages and currents directly to find the power. Now 5 into 60, this is 300. Now what is the apparent power? What is the apparent power in this case? See, apparent power in the sense I am going to calculate the apparent power associated with terminals 1, 3. Terminals 1, 3. Suppose this is 1 and this is 3. Let it be 1, 2, 3, 4. Okay. 4, 3. Terminals 4, 3. What is apparent power? How will you calculate the apparent power now? Root of P squared plus Q squared. But here I have not considered the reactance because I am going to find the apparent power this side only. So root of P squared plus Q squared equal to root of 300 squared plus, I am writing here, minus 720 squared. What is the value? Anybody? What is the value?
780
780. What is the unit?
volt ampere.
VA. So I am writing here VA. Now I am going to current IL and this one, reactance. What is my current IL? How will I find my IL? My IL equals S divided by, suppose I am taking, if I am using S, then what should be in the denominator?
ZE.
Now what is this value? What is the value in the denominator then? If I am taking S.
V, sir. Like
Suppose I am taking here 780. Because this is 780, right? Divided by what should be the value?
60.
60. Okay. So now I am getting 13 amps. But 13 amps is what is flowing through reactance. Now, suppose I want to find the voltage across reactance. I into XL, which is equal to 13 into, what is XL? Here 8, right? 8, which is equal to 104 volts. Now, the reactive power absorbed by the inductive reactance, if I want to find QL, what should be the sign of QL here? What should be the sign of QL in this case?
Plus, sir.
Plus. So I am writing 104 volt into, what is IL? 13, which is equal to plus, what is the value? What is the value? Is it 1352 var? 1352 var. Okay, so that is a value. Now the total reactive power absorbed by the circuit. I want to find the total reactive power absorbed by the circuit. So what was the negative reactive power? This QC is minus 720. This QL is plus 1352. Right. Now total reactive power, if I want to find, Q equals QL plus QC, but QC will take negative value. So the net reactive power is 1352 minus 720, which is equal to positive 632 var, which means in the circuit the net reactive power is consumed. Now, if I want to find the total active power absorbed by the circuit, which element is absorbing the active power here? Only one element is absorbing the active power, and that value is, what is the value? P itself, right? This one, 300. No other elements are there. So here 300 watt itself. Now I am going to find the total apparent power. Total apparent power absorbed by the circuit, which is equal to root of P squared plus Q squared, which is equal to root of 300 squared plus 632 squared, which is equal to 700 volt amperes. Now, what is the voltage of the line? How will you find the voltage of the line? Whether voltage of the line is given, it is just E. What is the voltage of the line? How will you find the voltage of line?
So 53.8.
How will you how did you get it?
700 volt ampere
This is 7
by
divided
30.
by IL, right? What is IL?
13.
Is equal to 53.8 or 9, I don't know, anyway, approximately. Now, impedance between the terminals 1 and 2. If I want to find the impedance between the terminals 1 and 2, this is 1, this is 2. The total impedance I want. How will you find it? How will you find it? Z total equals E21, that is between 1 and 2, voltage across the terminals 1 and 2 divided by IL, which is equal to, I got it as, what is the value? 53.9 divided by 13, which is equal to 4.15 ohms. Now, so this is what we do.
Sir,
Yes.
in previous section, sorry sir, I'm interrupting. Sir, power across capacitor, it is, I think, plus 720, sir. Because V is positive and IN positive, sir. I is also positive.
No, see, I'm not. It's not clear. Your voice. Can you ask a
Sorry,
bit louder?
voltage across capacitor is positive and the current direction also we taken as positive. How it becomes minus 720, sir?
No. See, this is power triangle approach. Okay, what we are doing here is, I'll tell you. See, here this is my S, this is my P, this is my Q. Now this is the theta. Okay, now if I compensate some partially, if I am compensating the reactive power, then which will give me a lower Q, right? So this is Q1, this is Q2, this is Q1 plus Q2. So initially the circuit has total reactive power consumption Q1 plus Q2. From this Q1 plus Q2, if I am which means your cos theta dash is now cos theta dash is increased or decreased?
Increase, sir.
Increase. So power factor is increased. So this is a kind of power factor improvement. So by connecting a capacitor with respect to power triangle convention, this consumption is considered as positive, and wherever generation is there, we consider it as negative. So that vector is subtracted from the positive reactive power. So that is what power triangle convention is, what is used here to solve the circuit. This is power triangle approach only, okay, of solving the circuit, because the final aim is to find the net reactive power. To find the net reactive power, we have to find the components which generate reactive power or deliver reactive power, and components which absorb reactive power, and we have to find the net reactive power. That was the approach here. Okay, so it's not based on voltage and current direction, not like KVL, I mean KCL. Okay, so that is what we used. Now one last problem. By this I will stop with this topic, active and reactive power. Tomorrow tomorrow slot is at 12:30, I think 12:30 p.m. I have already scheduled the meeting, the invited lecture by Dr. Kaushik of Mechanical Engineering on thermal power plants. So tomorrow's presentations will be rescheduled. Okay, anyway, we'll discuss that after the recording is over. Now I'm moving on to the next problem. Say I have a substation. Voltage is 12.47 kV, 3 megawatts, 2 MVAR. Okay, 3 megawatts and 2 MVAR. Now I have an inductor here. See, why I am showing an inductor here is that to represent a line. I want to represent a line. So to represent a line, I am showing an inductor here. Then I have a resistor like this. Then a load C, which is of, I'll do one thing. Let me, this I'm not showing now. Load C. Okay, load C. Okay, now 2.4 ohm, 15 ohms, and okay. So a single phase 12.47 kV transmission line, some kilometers long, we don't know, several kilometers long, feeds a load C from a substation. Now the line has a resistance of 2.4 ohms and a reactance of 15 ohms. Now instruments at the substation indicate that, you have some instruments here which indicates that the active and reactive power inputs to the line. So from here, P and Q, that is the input to the line, right? Active and reactive power inputs to the line are 3 megawatts and 2 MVAR respectively. Okay, now you are asked to find first the line current, and its phase angle with respect to, please mute your microphones everybody, its phase angle with respect to the line voltage at the substation. So now initially I am going to, how will you approach this question? You need to find the line current and its phase angle with respect to the line voltage at the substation. So if I know the apparent power delivered to the line, I have already obtained the measurements of active and reactive power fed to the line, I mean through the line to the load, right? So if I know the apparent power, I will get S. Then if I want to find the line current, I have the voltage at the input side, 12.47 kV. So from the apparent power, I can find the current. So S equals root of P squared plus Q squared. Can anybody calculate this? What is this? What is the answer here? Three squared plus 2 squared, which is equal to, what is the value? Anybody?
Sir, 3.74.
3.7 MVA. 3.7 or 3.6? 3.6 or 3.7?
3.74.
74. 3.7. So I'm taking it up to 1 decimal place, 3.7 MVA.
3.6.
3.6.
Yes, sir.
That is what, otherwise our, okay. Now what is the line current? How will you find the line current? Okay, somebody keep your calculators with you and find the answers for me. Line current, I equals, what is the voltage? So denominator should be voltage, right? 12.47 kV. That means 12470 volt. 3.6 MVA means 360000 VA. What is the answer? What is the answer here?
Sir, 288.7.
So can I take it as 289 amps? I'm taking it as 289 amps. Now, power factor at the substation. How will I find the power factor at the substation? How will I find? I can take P by S. Right. What is P? It is already measured from the substation, 3 megawatts. So I'm taking it as 3 megawatts divided by, what is my S? What is my S? 3.6. 3.6 MVA, which is equal to 0.83. Right, 0.83. Now you are asked to find the phase angle between voltage and current at the substation. Right, now you can find it. How will you find it? What is the phase angle? Cos inverse 0.83. What is the phase angle? Can somebody calculate it for me?
34 degree.
34 degree. Good. So I'm going to draw my vector. This is my voltage. Let it be the reference. So I'm getting my current like this. That is 289 amps. 289 amps. and my voltage is 12.47 kV, and this is 34 degree, right? Okay, now in the second part you are asked to find active power dissipated in the line. Active power dissipated in the line. So this is your line. Your line has both R and X, right? So after load will get the active power after the dissipated active power is subtracted from the input active power, right? Load will get that much active power only. And what is the reactive power input to the load? Some reactive power is already consumed by this reactance. The remaining only we will get. Now, what will be the voltage across the load terminal? That also, to get that, we have to subtract the drop across the line, voltage drop across the line. So with this, I am going to find the active power dissipated in the line. Okay. PL I am getting as, so I have resistance as active component, and resistance is 2.4 ohms. Reactance I am not considering because I am trying to find the active power dissipated only. So PL equals R into I squared, which is equal to 2.4 into 289 was the current squared. What's the value? What's the value here?
Around 0.2 megawatts.
0.2 megawatts. Good. Now, active power absorbed by the load. How will I find active power absorbed by the load? How will I find?
So 3 minus 0.2.
Yeah, 3 minus, good, 0.2, which is equal to 2.8 megawatts. So I got active power absorbed by the load. Now, if I want to find reactive power absorbed by the line, QL equals, I have to take XL into I squared, and 15 ohms is the reactance into 289 squared, which will give me 1.25 MVAR. Okay, now D, apparent power at the load, apparent power at the load. How will I find apparent power at the load? How will I find apparent power at the load? See, my load is
1.25.
Yeah, so my load is I'm assuming it as C, right? Load C. It is named as, titled as C. So PC squared plus QC squared. I have already found the active power absorbed by the load and reactive power absorbed by the load, which will give me root of 2.8 squared plus 0.75 squared, which is equal to 2.9 MVA. Now I am asked to find voltage at the load end of the line, or the terminal voltage, because load voltage. Obviously there is a drop on the line, so the remaining voltage only I'll get across the load terminals. So load voltage, I am representing it by EC, which is equal to apparent power of the load is SC divided by current. See, please. Anant Singh. Okay. See, I think somebody is playing songs. Okay, fine. SC by I. So equals 2.9 MVA divided by 289 amps, which is equal to 10.03 kV. Okay. Now F, power factor at the load end. power factor at the load end. So what you should be careful about in calculating the power factor is that from the substation side, if you look from the substation side, then this whole thing is an impedance, right? So this has a power factor, but normally we associate power factor with the load only because line is always there. We are connecting different loads at different times. So based on that, your power factor varies. So now, it is important to find the power factor of the load. Power factor is always defined from the load side, but when you view from the substation side, the whole impedance, including the line impedance, will come into picture while calculating the power factor. But here you are asked to find the power factor at the load end only. Okay, so if you want to find it, you can PC by SC. C is your load, PC by SC, which is equal to 2.8 megawatts divided by 2.9 MVA, which is equal to 0.965 or 96.5%. Now, the phase angle between voltage and current at the load. Phase angle between voltage and current at the load. That is why I'm putting this C here, which is equal to theta C equals cos inverse 0.965 equals 15.2 degrees. So it follows that the phase angle between the voltage at the substation and that at the load. What is the phase angle between the voltage at the substation? Initially we found that, right? Voltage and current at the substation. Where is it? This theta. This is 34 degree. This is 34 degree. Right. Now, across the load, it is 15.2 degree. So if I am taking load only, I am getting, this does not look like 15.2 degree, but fine. 15.2 degree, 10.03 kV is the voltage, 289 amperes. So this is my load and phasor diagram. This is my substation phasor diagram. Okay, with voltage and current. Now, so this is what using vector algebra also we could have found out the these values, but we used just active, reactive and apparent power to find the phase angle in this case. This is a simple approach, a power method to solve the circuit. Now I am going to stop my recording.